we call relations and functions. A relation is just a comparison or some sort of connection between two things. Okay? And in math, we just call it a relation. Don't know why, that's just the definition of it. Okay? So there's a few examples right here of different relations. So if you talk about the value of a computer versus the age of a computer, right? The older a computer gets, the less it's worth, typically. Right? Same with a car. Right? The longer you've had the car, the older it is, the less it's worth. That's a connection between two mathematical things. We call it a relation. Right? A couple of more examples. They said the price of watermelon is related to its weight. The bigger the watermelon, the more it's going to cost. Right? The smaller the watermelon, the cheaper it's going to be. Unless you buy those square watermelons. Seen that? That's cool. They make like square watermelons in China. They grow them in boxes. Oh, we'll Google that at the end of this. And then the last one they have here, the time taken for a person to walk to school is related to the distance they have to walk, right? So if I live right next to the school, I don't have very far to walk. It doesn't take me very long. That's a relation, right? The further away I live, the longer it's going to take me to get here. Makes sense. Okay. We'll list one more because it says to. Oh, maybe not. There we go. An example of a relation, I'm going to say, let's do something that they haven't used. Let's do the price of a house to square footage. Oh, I like it. That's such a good one. Price of house. That's a really good one. I kept thinking age ones. I didn't want to go with age one. Price of house to, I'm just going to put size, but square footage is definitely the proper way to compare them. The bigger the house, the more it's going to cost. Most likely, right? Like there's always the odd case where it's a little special. But that's definitely a relation. That's a connection between two mathematical. Awesome. Representing data or relations. There's a lot of different methods to connecting things, to connecting numbers. Here's a whole chart of everything we're going to do. So we're going to talk about connecting relations in words, using something called a table of values, something called an ordered pair, which we did a little bit yesterday, a mapping diagram, we haven't seen much of that, an equation, a little bit of that yesterday, a graph, we did a little bit of that yesterday, and function notation, which we will do at the end of this unit. All right, so these are all the different ways we're going to learn how to represent things. The ones that are really important. Probably a set of ordered pairs, a graph, and an equation. Those are probably the three that we see the most of moving forward. And then function notation once we start learning it. Keeps on going. We don't do a lot of in-word stuff. We don't do a lot of mapping diagrams. They're kind of slow and messy. And we don't do a lot of table of values. Again, they're kind of slow and messy. So the biggest ones that we learn are the ones that we've highlighted right there. But you will need to know all of them. Awesome. We're going to look at this question. Well, yeah. So they gave us a relation here. They talked about the cost of driving versus the speed. Right? So the cost C of driving a car is related to the speed S at which the vehicle is driven. The faster you go, the more gas you burn. Right? That's going to make it more expensive. So that's the relation. Faster, more expensive. Slower, cheaper. We'll use this relation to introduce some ideas, and we're going to learn a couple definitions. Okay, the first definition we're going to talk about is the word variable. You've heard the word variable before. We've already used variables before, so hopefully that's something new. Variables in the past to us were like x and y. Right? We have an equation. There's x's, there's y's. We did it in trig, right, where we had opposite. We would call it x or something, and that would be a variable. In this question, our variable actually represents something. So our variables are C and S, which actually represent something. C is the cost of driving your vehicle. S is the speed of your vehicle. So when we do this unit, the variables will actually mean something, like something applicable, instead of just being like a number, which is what we're kind of used to. These two variables have specific names. And one of them will be called the independent variable, and one of them will be called the dependent variable. And it just depends on a couple things, mainly the situation, and then how you organize your work. So as we get going on, you'll see that you can kind of flip it around and make one independent, one dependent. In this case, though, it's pretty clear which one is the independent and which one's the dependent. If we think about it, the cost of driving depends on how fast I'm going. I choose my speed. Right? Like I'm going to go take my car and I'm going to choose how fast I want to go. That makes that the independent variable. I think it says that in the notes. See if I can spell independent. It's independent because I'm choosing it. Like I'm selecting a speed. Then the cost changes depending on what I've chosen. This depends on what I chose. So it's the dependent. I believe it says it down here. C is the dependent, S is the independent. When I think about it, I'm like, okay, which one of these is dependent, which one of these is independent? In any question, I think about which one's reacting to what I've chosen. The cost of me driving reacts to the speed that I've chosen. It's not the other way around. I don't choose a cost that I want to run my vehicle at. And I'm like, okay, I want to burn 37 cents or 37 liters per hour or something crazy like that. I have no idea how I would decide that, or if those numbers made any sense. But I don't choose a cost and then start driving at that speed, right? It's the other way around. Awesome. These two can also be called something else, because why not make it even more confusing? They can be called input and output. Your independent one is your input. Your output is your dependent one. Again, it does say that in your thing right here. The independent variable is the input, the dependent is the output. I like to think of it as independent input, in and in. I'm not very good at using this terminology, independent, dependent, input, output, but I'm going to try to get a little better at it so you get used to hearing it more often. All right? Because the more you hear it, the more likely you're to use it as well. Awesome. The last thing that we're going to talk about, I'm pretty sure for definitions, is something called domain and range. Did you guys do domain and range last year? I don't think you do. No, that doesn't ring a bell? Okay, that's good. We're going to do a whole bunch of work with domain and range later in the unit. Domain is just a way of describing your input values, and range is a way of describing your output values. We're going to do more on that later. Okay, so don't worry, like this stuff we'll do later. Don't worry too much about that. We'll have a whole lesson on just that. Fantastic. Here, they've given us a whole bunch of input and output values. So they've represented it in different ways. I'm trying to get it so I can see everything. Doesn't quite like that, does it? Why is this up so big? So big and bulky. Okay, we're going to look at this set first, this table of values. This is one way of organizing your data, your input and your output values. A table of values shouldn't be new to you, right? You should have seen this somewhere, probably in science class, right? Science classes love to use these types of tables. It's a nice way to organize your data and to directly look at numbers. Right? A table of values starts off with having two columns and two headings on those columns. The input is your speed, so this is speed, and this is your cost. Then you see a bunch of pairs of numbers. This first pair tells me that when I drive at 20 miles per hour, I have a cost of, I think it's 10 cents per hour. Let me look up. It didn't really tell you, it just says it's cost. Yeah, kilometers per hour. Did the other one say what the cost was?
Like on the graph, cost of C.
Oh, it's cents per kilometer. Okay, so yeah, cost is cents. So this is saying if I drive at 20 kilometers an hour, it costs me 10 cents per hour. The next one tells me my next thing. It says if I drive at 30, it costs me 9.1. If I drive at 40, it costs me 8.4. And these are all pieces of data that connect to each other. So on a table of values, whatever's directly beside it, that's what's connected to it. I don't use a lot of table values. We don't see a lot of table values in math. We see a lot of things called ordered pairs, which means they take these things and then they write them like this. So instead of it being in a nice table of values, they put it in brackets with a comma sitting in between it. That's the stuff we saw yesterday, right? Typically we see it as XY, X, comma, Y. But technically, those letters could be anything, right? As long as it's an independent and a dependent, or an input and an output, you could put it in an ordered pair and write it like that. Once you write it in an ordered pair like this, it goes onto a graph really easy. So if you look at an ordered pair like 20, 10, you'll notice that you could plot that on a graph if you came over here and you went to 20, speed of 20, cost of 10. Right, there's my point right there for 20, 10. That's organizing your data on a graph. Again, we did some of that stuff yesterday, right? We took ordered pairs, we put them on graphs. These are just different ways of connecting the same things. These are three things you've probably seen a lot of. Like, you've probably seen a lot of table values, a lot of ordered pairs, and a lot of graphs. My guess. The ones that don't really fit. Mapping diagram. A mapping diagram really doesn't connect well with any of that stuff. We rarely use them. You maybe saw it in science class. They like to use it in science class, usually with words, not actual math data, but they like to connect it with words. How a mapping diagram works is that you take your input and your output, and you put all the values inside a bubble from lowest to highest. So here's all my possible inputs in this bubble. Those are all the different speeds that you drive. Then they make a bubble with all your possible costs. They're like, okay, here's all the different costs that I could get. And they order them from lowest to highest. You'll notice that both bubbles go from the smallest number to the highest number as you go down. And then a mapping diagram uses arrows to connect your input to your output. So you'll notice it says if I have a speed of 20, follow the arrow, it'll point to my output of 10. Speed of 20, output of 10. Speed of 30, follow the line, output of 9.1. Okay, the arrow is always going from the input into the output. That's how mapping diagram works. Again, we rarely ever use mapping diagrams, mainly because it's messy, right? The more pieces of information you have, the messier it gets, the bigger it gets harder to read, harder to understand. You guys seen those in science? They use those? No, not really. Sometimes they use them to connect like hair color to eye color, stuff like that. They're a connected piece of data. It's usually not with numbers because it's just too messy with numbers. Awesome. The last one we haven't talked about, this is the last one, is an equation. Okay. Yesterday we did a little bit of equation work. We were building those linear equations, that's what it's called. They were very simple. They were describing two things in some sort of format, right? Yesterday we were doing toothpicks and triangles. Anyway, every time we got two more toothpicks, we got one more triangle. Okay, we created an equation out of that. You could do that for almost any mathematical relationship. So for this one, the cost and the speed creates an equation like this. That's a pretty complex equation. Okay, so that's called a quadratic. You won't need to really know that until next year. However, there is something important that you do need to notice in here. The output value, C, is all by itself. It's on one side of the equal sign all by itself. And the input value is with everything else, with all the numbers and everything else on the other side. Okay, that's not a coincidence. So that's going to be probably one of the few important things you need to know right now. Output is isolated. The input has all the numbers around it. If you look over here, these are my input values. And they're the same ones. Okay, so if I say the speed is 10, then I would make both of these input values 10. These equations directly correlate to creating graphs. So this equation would make this graph, this curvy line. They're connected. For every single speed that I could choose, every little decimal, right? So 10, 10.1, 10.2, 20, 30, 40, 50, I would get a different cost, and then I would connect all those dots to create these lines. The reason I'm connecting is because it's continuous data, right? My car doesn't just instantly go from 10 kilometers an hour to 30 kilometers an hour. It gradually grew to that point, which means I have a continuous relationship, which is why I can connect these dots. It's why this graph and this equation can connect to each other so nicely. Awesome. That's a lot of definitions thrown at you, right? And then connecting a lot of information, all just kind of thrown at you. Awesome. Oh, so one thing we didn't mention, your input and your output on a graph. This one will always be your input. So input is your X, right? It goes along the bottom. Output is your Y. It always will go up, down, like that. You do need to know that as well. Input bottom, output on the side. I just was forgetting that one little piece of info. This basically just summarizes what we said. It's a good recap, right, or summary. So if you ever forget, you're like, oh, I don't remember what a mapping diagram is. I don't know which one's the independent. I don't know which one's the dependent. I don't know input. I don't know output. This kind of summarizes it all. So it talks about order, pairs, table values, mapping diagrams, graphs, and equations. Right? So it's all there for you if you forgot any of it. So it's kind of like your space to check. Like, oh, right, that's what it is. Fantastic. Now let's look at an equation. This, again, is a beautiful little summary of what we just talked about. They built an equation for you here, and then they've told you everything you know about that, definition-wise. So this is y equals 3x minus 5. You'll notice that y is by itself. It's isolated. Because it's isolated, that tells us it's the dependent variable. The dependent variable tells me it's also the output variable. Right? Just two different ways to describe the same thing. We describe the outputs using a word called range. Again, you're going to learn about range in the future, so I wouldn't worry too much about that. Oh, I thought I saw the word range on this page. I didn't? Okay, good. It's the second coordinate in an ordered pair, and it's the vertical axis on a graph. Right? Just a nice little summary of everything you know when you look at an equation. X has all the numbers around it, meaning it's the independent variable. Independent tells me it's the input. when I know something's the input, that makes me think of it as being like the x variable. X goes first in an ordered pair. X is the horizontal axis across the bottom of the graph. Again, just like a summary review of everything we just talked about. Just nicely organized for you. Awesome. In these diagrams, we are going to figure out which ones are the independent, which ones are the dependent, and then we're going to list them. Okay, and they gave us 3 different ways of ordering things. So this first question is a mapping diagram. Oh boy, that's not a nice little diagram. What did I just do? We're learning things. We're learning things, people. Okay, that's a mapping diagram. I know it's a mapping diagram because it has bubbles and arrows. Okay. We're going to figure out which one's the input, which one's the output. Okay, the input is the one that has the arrows pointing away from it. So looking at this, that means this is the input. Because the arrows are coming away from it. I choose one of these numbers, I choose 8, and it gives me an output. It points to something else. This is the output. If I did it the other way around, and I chose 16, 16 doesn't give me anything because the arrows are coming into it, not out of it. So I can't figure out where it would actually connect. Okay? These are my input values, these are my output values. We could write them out if we want. I don't think you need to. The inputs are 5, 8, and 11. The outputs are 10 and 16. Awesome. Looking at the second one. The inputs and the outputs on a table of values. Right? That's what this is called. Table of values. The first thing is your input. So my inputs in this case are 4, 10, and 25. My outputs in this case are 15, 12, and 15. And again, for a table of values, these things go side by side. So an input of 4 gives me an output of 15, input of 10, output of 12, input of 25, output of 15. They pair up in a table of values. Nice and simple. The very last one we have here, this thing is called ordered pair. In an ordered pair, the first thing is the input, then you go comma, output. Hopefully it did work output. So in this case, the inputs are 3, 4, 5, and 6. The outputs are 7, 11, 15, and 8. The second numbers in each ordered pair. Not bad, right? Hopefully. Just boring definitions, not very exciting. We have 2 more here. Okay, we have an equation and we have a graph. We're going to state the input and the output for each thing. Remember, input, output means independent, dependent, same idea. Okay, so if you're looking at this equation and you're trying to figure out which one's the independent and which one's the dependent, in an equation, the one that's by itself, this guy, that's the dependent or the output. The variable that has the numbers attached to it, which is R. That's the letter with the numbers attached to it. That is our input. So in an equation, output by itself, input's what I'm choosing, which is next to all the numbers. On a graph, the horizontal one that goes side to side, that's our input. The vertical one, the one that goes up, down, that's my output. Again, independent means, or input means independent, output means dependent. So those words can be interchanged and it would still make sense. Awesome. This last one, C, is written in words. So it says the amount of sap, S, obtained from a maple tree is dependent on the time, T, a container is left attached to the maple tree. We're going to figure out which one's the independent, which one's the dependent, or which one's the input, which one's the output. Okay, we have the amount of sap that you get and the amount of time that you're tapped into the tree. Which one of those things are you choosing? You're choosing the time, right? You choose how long you're going to be in that tree, right? Trying to drain that tree. Because you're choosing time, that makes it your input. Or your independent. Your output is the result of the time that you chose. Okay? That means that this, the amount of sap, is your output, or your dependent variable. Again, it just depends how you want to discuss those terms. Fantastic. I think you guys are getting it. It's not too bad, hey? It's kind of just definitions. Ordered pairs. So we're going to look at some ordered pairs. We're going to use an equation. When we use the equation, we're going to create a graph after we use the ordered pairs. So you're going to kind of see what I mean. Example number 4. Consider the relation described by this equation. So they tell me y is equal to 2 times x minus 5. If we used outputs and inputs, that means my output value is equal to 2 times my input value and then subtract 5. They've given us a table of values right here. They filled in my input values or my x values. What we need to do is fill out the output values and the ordered pair values. To get an output, when using an equation, you take this value and you put it into your equation. So instead of saying y equals 2x minus 5, we're going to say y equals 2 times negative 2 minus 5. And then we're going to calculate what our output value is when we have an input of negative 2. We're going to do it a bunch of times here. So the first input value is negative 2. I'm going to go back to my equation. My equation says y equals 2. Instead of an input value x, I'm going to now put a number in. Negative 2 minus 5. There's my equation. I changed my input value to be negative 2. That's why I put it in blue. Now you can calculate your output value. This thing right here can go in my calculator. I'm going to go 2 times negative 2 and then minus 5. And that will tell you that your output value, when you have an input value of -2, is -9. When I have an input of -2, I have an output of -9. As an ordered pair, we write that as -2, negative. Input goes first, output goes second. We'll do another one here. Our input value is now -1. So I go back to my original equation. I go y equals 2. Instead of x, I put -1 and then -5. I now have an output value and something I can calculate. So I'm going to put this in my calculator. When I calculate that value, 2 times -1 minus 5 is -7. So that means an input of -1 gives an output of -7. That means I have an ordered pair at -1, -7. I want you to try to fill out the rest of this chart on your own. If you want to do 3 and 4 as well, feel free. Okay, so give it a shot. Alright, so you should hopefully have that chart at least a little bit filled in. You can check your answers with mine. So I put mine up on the board. I put all the outputs, and then I put all the ordered pairs. You might notice that your outputs actually followed a bit of a trend, and it's because this was a linear pattern, and it was just going up by 2 every time, which is the pattern that happened. We'll talk more about those types of patterns and how you can figure that stuff out later. But for now, the important thing is you understand that you can take an input, use it with an equation, get an output. When you get that output, you then can create an ordered pair. This. The reason creating an ordered pair might be beneficial is then you can graph that thing. You can graph all those ordered pairs. So that's what we're going to do. We're going to take these ordered pairs and we're going to put them on this graph, this Cartesian plane down here that they left us. So we're going to go down here. We're going to plot -2, -9. That's our first one. All right, remembering how a Cartesian plane works, you start at the center at 0, 0. The first number, the input, is my horizontal, my left to right. It's -2. That means I go 2 to the left. Then I use my output value to go up or down. So my second value goes up or down. It's -9. That means down 9. My first point is right here. -2, -9. First value left, right. Second value up, down. The second order pair we had was -1, -7. The first number tells me how far left or right to go from the center. From the center, I need to go -1. That means 1 to the left. The second value is -7. That's telling me how far up or down to go. Since it's negative, I go down 7. My second point is right here. -1, -7. And we can keep plotting those points. We would have 0 and -5, 1 and -3, 2 and -1, 3 and +1, 4 and +3. So you have all those points right there. So we now have taken an equation, created a table of values, created ordered pairs, created a graph. Right? It all connects together. Because this is an equation, and this equation has no context to it, we're going to assume it's continuous data. Because it's continuous data, that means that we can connect the dots. So for this equation, we can connect all these dots, kind of like this. Like that. And again, I would use a a straight ruler if I were you. I can't on my smartboard, but you should use some sort of flat edge so that your line is nice and straight. The reason that that line needs to be nice and straight and that you're connecting all these dots accurately is you can now use this graph to figure out more inputs and outputs. What I mean is that any spot on that line should give you an input and an output. For instance, let's just randomly pick one. Let's go right here. This random spot that's on the line tells me that my equation has an input of 8, because it's 8 to the right, comma 9. And because that's on my line, I know that's an input and an output value. Your line has to be accurate for that to actually work properly for you. I think in this case, my line's not very accurate. It should be 8, 11. Yeah. So if you have a nice accurate line, it would be 8, 11. My line's a little bit slanted because I didn't use a straight edge. So make sure you're using straight edges to draw those lines. Okay? Let's answer a couple questions so you can see how this works. We'll get rid of that random point that meant nothing to us. Part D. Use the graph to determine the value of y, so figure your output, when you have an x equals 6, input of 6. So what I need to do is look on this graph and ask myself, when do I have an x value of 6? X equals 6 right there. I need to figure out where on this graph I've gone that far to the right. If you look at this graph, right about here, it appears that I've gone 6 to the right. Again, my graph's a little bit off, isn't it? It should be 1 up. It should be at 7. Yeah. So if you drew your graph accurately with a straight line, you should be at 7. Mine's at 6 because I didn't draw a straight line because I don't have a ruler. Right? But input of 6, check on the line where I am, gives me an output of 7. That means 6, 7 is a point on my graph. You could do that over and over and over and over again. Right? I can give you this graph and just keep asking you, what's your input when you have this output? What's your output when you have this input? So on and so forth. Use this equation to determine the value of y when x equals 6. We already did that. Oh, use the equation too. We could do that. I don't think we need to. We've done enough with the equations. Okay? The big thing is how to read a graph now. Does anybody have any questions on that? Did that make sense? Clear as mud? Good. Okay, I want you to try one on your own. So, oh, they have more questions then. No, wait, use it. Oh, we should do G. I like G. It just shows you can go the other way, right? So G is saying determine the value of x, so figure out what input would give you an output of 3, a y value of 3. It's the same process, except reverse. Instead of using your horizontal, you're going to use your vertical. So looking at my graph, they're saying that my output was 3. Output is y. This is 3 right here for my output. I need to figure out where on my line I have an output of 3. In this case, it would be at 1, 2, 3, 4. I have a point at 4, 3. So an output of 3 happens when you have an input of 4. You can use the graph to just go the other way. The yellow's a little hard to read on that grid, isn't it? I apologize for that. Awesome. The last one says the relation is called a linear relation. You've heard me say that a bunch of times already. It's a linear relation because it created a straight line. Not that complex of a concept. straight line, linear. I want you to try this one on your own. Okay, so you have an equation here. They gave you a bunch of inputs. See if you can fill out this whole table. So give it a shot. And if you've done that really quick, you can try to do the graph below, but we will do it in pieces together. Okay, so to fill out this table of values, I had to take my equation, which is given right here, and I had to put my input values into that equation. Okay, I had to do it 1, 2, 3, 4, 5, 6, 7, 8 times. There wasn't a real pattern here that you could follow. You just had to actually do the math. So when I do the math, I look at my equation, I go y equals, and instead of x, I put my input value, and I put it in brackets. And then I have squared minus 6. If I calculate this, so put that part in my calculator, that tells me my output when my input was 4 would be 10. That gives me my first point at 4, comma 10. And you should have done this over and over and over again to fill out the entire table of values. Your point should have been 3, -2, -5, -6. We're ready to do the next ones together. That gives me all these ordered pairs. 3, comma 3. Gives me 2, comma -2. Gives me 1, comma -5. 0, comma -6. The reason I want to do the next ones together is because they're negative. And sometimes we make mistakes with our negatives in our calculators. We talked about it in Unit 1, right, but maybe we forgot. Okay, the trick is that you have to use brackets. So if I do an input value of -1, I need to put in brackets like I have right here. And the brackets have to go into my calculator. If I don't use brackets, my calculator will actually make a mistake. The reason why is the brackets tell my calculator that the base is -1 squared. Without the brackets, you're saying negative times 1 squared, which is different. Okay? You must use brackets like this. When you do that, you end up getting a y value or an output value. Down a little bit. An output value of -5. Yeah, for sure. You too, yeah. Okay, make sure you're using brackets with negatives. Probably one of the easiest, biggest mistakes we make as math students. That means my points are at -5, -2, 3. I'm just going to fill in those ordered pairs now, and I'll give you a chance to maybe fix yours if you fell for that mistake, which I bet at least half the class did. It's a super common mistake. It continues to happen at the Math 20 level and Math 30 level. Fantastic. Your order of pairs should now match my order of pairs. We can now take ordered pairs and put them on a graph, right? The first value tells me how far left or right. The second value tells me how up or down. So this first ordered pair of 4, 10 means start at the center of your Cartesian plane, or the center of your graph. Go 4 to the right, and then go 10 up. 4 to the right, 10 up, gives me a point right there. My next one was 3, 3. So 3 to the right, 3 up, 3 to the right, 3 up, right there. My next one was 2 to the right, and then I think -2. 2 to the right, then 2 down. Then I had 1 to the right, and then 5 down. 1 to the right, 5 down. Then I had 0 and 6. And then I kind of went the other way. And you should have all those points on your graph. Actually, I think that last one you don't have that. But I just know it's there. Hey, there's all my points now put onto a graph. Because this is an equation, and because we have no context, we can assume that this is a continuous piece of data. Right? An equation now can have all of our lines connected. So what we do is we put a little bit of connect dots. Looking at this, it looks like I'm making a little bit of a pattern. We're going to go down. I can't see because of my shadow. Something like that. And I create kind of that loop. My picture is not very good. Try your absolute best to connect the dots. It's not easy with these questions. Okay, but try your absolute best to connect your dots in some sort of nice fashion. Some of you will be really good at it. Some of you will be like me. Not very good. Awesome. We can then use that system to try to predict things. Okay, so I want you to try to answer these questions. Figure out your output when your input's -4. There's one a little lower where they give you an output, figure out the input. Okay, so try and see if you can do that. Give it a shot. Okay, let's just talk about what this says. So it says use the symmetry of the graph. Don't worry about the word the symmetry, just use the graph. So use the graph or table to predict the value of y when x equals -4. What they've given me is an input of -4. They're saying go 4 to the left. And then figure out where on your graph you have a point that's 4 to the left. On my graph, all the way up here, I have a point that is 4 to the left. Okay. I went 4 to the left and up until I hit the graph. That gives me a point at -4, 10. So I can just use that graph to figure out my output when I have an input. I can then confirm that using the equation. You don't need to. If you want to, that's great. You should have found that it still worked. Okay, so if you did -4 squared minus 6, you should have got 10. And you should just confirm that using your equation. You can write that in table of values if you want. Connect the points. We already did that. The last question, why do you think this type of relation is called a nonlinear relation? Okay, so there is a more particular name for that type of graph. That's more next year. We just call it nonlinear. That's how we refer to it. The reason we call it nonlinear is because it has a curve in it. Okay? When it has a curve in it like that, we say it's a nonlinear function. Looking at the equation, we know it's a nonlinear equation because it has a degree of 2, meaning that the highest exponent was 2. Right? When you're looking at an equation, linear equations have a highest exponent of 1. All we need to know for now is it has a curve. Has a curve. Has an exponent. Other than 1. Right? If there's a square exponent, a cubed exponent, any exponent other than 1, it's not linear. Fantastic. If I